What if I told you that with a hunk of coax and something to wind it on, that you could stop RF of a certain frequency from traveling down a wire? This time in the shack. Okay, so this is basically an extension of the last video because I talked a little bit about putting a trap in an end-fed antenna. And by doing that, we can block 7 megahertz RF from making it to the end of the antenna, and we can create an antenna that works on fundamental frequencies of both 7 megahertz and 3.9 megahertz, which gives us an NVIS end-fed that works good on both of those bands. So 40 meters and 80 meters both. And this is all theory, but I'm thinking I have a 40 meter end fed up in the air. I might as well just go ahead and build this trap and add some wire to the end of that antenna and see if this actually works. Now, one caveat. I mentioned in the last video that this antenna should work on 20 meters. And by modeling, I don't think that's going to be the case. So real quick, I'm going to run an SWR plot, and I'm going to run this from 3 megahertz up to 29 megahertz. And I just want to see what this antenna, or where it will actually be resonant. I was hoping for 20 meters, but in this case, it looks like 20 meters is not going to be feasible. So here is 7 megahertz, there is 3.7-ish megahertz, and here you can see our problem. So 14 megahertz is right between these two resonance dips, and it's actually not going to be resonant on 20 meters, unfortunately. But what I did find is it's going to be resonant on 15 meters, and that 27.4 megahertz doesn't do us any good unless you have a CB that you would like to experiment with. But 21.6 megahertz, and if we look at the low part of the band here, this thing is reachable by the tuner and the radio over the entire 15 meter band. So we could make this antenna resonant on 20 meters by adding a coil or an inductor somewhere in the antenna. And the way that you would do that is, if you say you wanted this to be resonant on 14.2 megahertz, what you would do is you would try and place that coil in the part of the waveform on 14 megahertz where there's high voltage and low current. And the reason you would do that is so the coil would have very little effect on 14 megahertz, but on the other bands, you would see there's quite a bit of current through it at that point, and it would have an effect. The same thing would be for 80 meters. You see, if we placed it in that high voltage, low current spot for 20 meters, it would actually be a pretty high current spot for 80 meters. And what would happen is it would make the antenna too long for 40 and 80 meters, and you'd have to shorten it a little bit. And that would change your resonance point for 20 meters because the coil wouldn't have an effect on 20 meters. A common coil for that is 5 turns on about a 3-inch form, and it gives you just enough inductance to change things to kind of move your resonances around. But you can experiment with that if you want. You just have to make sure that you put that coil in a place on that antenna where the band that you want to change, it has very little effect. So at the high current, low current, or high voltage, low current spot. And then it would have very little effect on that band. But all the other bands that would have an effect on it would essentially make them too long, and you'd have to shorten them. So you could change the resonance of the antenna to make it work in that fashion. But for me, I'm not worried about 20 meters. I've got a 20 meter dipole up on the tower. But it would be nice to have 15 meters. So let's go ahead and see what we'd have to do to make this antenna work on 15 meters. So the pattern looks like it's pretty good. It's not horribly great, but it's not horrible either. But the main purpose of this antenna is to give me an NVS antenna that works well on both 40 meters and 80 meters, which it should do nicely. We'll know. Okay, so the first thing we need to do is I'm going to be building this with RG58 instead of RG174 because I thought I had some RG174 tucked in a drawer somewhere and I just simply couldn't find it. So this is just RG8, or I'm sorry, RG58. This is RG58. And what I did is I know from the K7MEM site that I need about 9.4 turns. So I wrapped 9.4 turns around an 1.5" form, and then I cut off the excess and I stripped the ends. Now what we have to do is we have to see if this generic RG58 that I don't know the specs of equals what the K7MEM site gave me. So right off the bat, I want to change my specs from the numbers that I entered before and change it into the new specs of 148.8 picofarads, 148.8, and our new microhenry reading is 3.5. So this is for the RG58, quote-unquote theoretical RG58 that I have. And then I'm going to run an SWR sweep and just see if anything changed. And it looks to be roughly the same. 20 meters is still hosed. 15 meters still looks good. So once again, we add a little bit of capacitance, we took away a little bit of inductance, ended up at the same resonance. Okay, so the way that I'm going to do this is I have a couple pieces of 1.5" PVC. This one just happens to be sewer pipe, but you can use anything. I have 2 pieces. So this first one, I've already wrapped 9.4 turns of this coax on it, and I've drilled holes in it where those turns end. So what I'm going to do is I'm going to go ahead and wrap 9.4-ish turns on this form. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the leftover. You'll notice that I've drilled this hole down here, so it doesn't end on a full turn, it ends on a partial turn. So in this case, about 9.25 turns. I'm going to feed that through. And pull it tight. And that's basically what a coax trap looks like. Now, if you're wondering how these work, let me go into this real quick here. So basically what we're doing, if you look at coax, the schematic for coax looks like this. We have a series inductance, and then we have a shunt capacitance. So series inductance, shunt capacitance, and that just repeats. And that's basically how you draw the schematic for coax. And it just keeps on going. So we have a capacitance value, and we have an inductance value. And as I mentioned in the transmission line video, the way that works is as the RF travels down the coax, those inductance and capacitance values manipulate the phase of the RF to keep it in phase. So if it starts to drift a little bit from inductance, the capacitance brings it back in line. And it just keeps doing that. So that's how it works. So traps, on the other hand, aren't a series inductance and a shunt capacitance. What a trap is a tank circuit. So a tank circuit is a parallel inductance with a parallel capacitance. And what's cool about that is at one frequency, one specific frequency, what will happen is this thing will absorb all of the energy being presented to it, and it will be resonant or oscillating. And when that happens, the capacitor will give up energy, the inductor absorbs it. The inductor gives up energy, the capacitor absorbs it. So tank circuit. No energy can go through this when that's taking place. It just circles in there. So the energy just goes in a circle. And there are some losses that we won't bother to calculate because it's irrelevant. But for our purposes, what happens is at one specific frequency, this thing becomes a very high impedance. When it's oscillating or resonant, it becomes a very, very high impedance. It effectively blocks any energy from traveling through it. So we can use that to actually block RF, and we can design it to work on a very specific frequency. In this case, we're building this one to work on 7 megahertz. So we're reconfiguring this coax so that it's no longer a series inductance and a shunt capacitance. What it is a tank circuit. And the way that we do that is the input of this trap is going to be the shield. So what's coming out of our transmitter, what's coming out of our radio, the wattage that's coming out of this radio is going to go in this wire. Now, granted, there's going to be some wire before it, but the feed point's going to be off here too, but it's going to go in this side of the trap. And it's going to go around this trap 9.4 times. And it's going to come out on the other side. And then what we have to do is we have to take this shield where this RF energy came out, and we're going to bring it right back. And at that point, it's going to go in the center conductor. So we're going to connect the shield coming out the other side to the center conductor of this coax. So to start with, I'm just going to twist this, because at this point, we're just testing this coax to see if it's the right capacitance for what we want to do. So I'm just going to reach in here. I'm just going to twist the center conductor and the shield together. In the finished product, this will be soldered. Okay, like that. Not the prettiest job in the world, but all we want to do is make a connection there. So, the shield is our input. RF goes in the shield. It goes around 9.4 turns. Comes out the other side on the shield. We run that shield right back to the beginning and put it on the center conductor, and it goes around the center conductor 9.4 times. And then the center conductor becomes the output. So this wire would be the input, the shield would be the input, and then the center conductor becomes our output. This goes to the rest of the antenna. That's all there is to a trap. That's how they work. So I'm at the point now where I can actually test this thing. All I need to do is hook up the device that I built in a previous video for doing exactly this. So you can configure nano VNA to be used like a grid dip meter. It can perform that function just by creating a little coil of wire. And it will work as a grid dip meter just like that. So let's see where this one is resonant. And all we have to do to test this is we just drop our trap in the middle of this thing. But I need to pick some frequencies and calibrate, so. Okay, now we are calibrated. And you can see on the nano VNA a very sharp resonance. So let's figure out what that frequency is. And it looks like this trap is resonant on 6.680 megahertz. So it's quite a bit low on frequency. And I expected that. Typically when I build these, they are low on frequency. I don't know why. It just seems to be the case. Now, here's a way you can cheat. You can actually grab the windings of this trap, and you can just kind of separate the windings a little bit, and that will shove it higher in frequency. All I want to do is see how sensitive it is to that. And it didn't change it much. It moved it from that 6.680 up to 6.840. And where we want it to be is, well, I don't know, this is awfully close. I think what I'm going to do is take about 1/8 of a turn out of this. And I think we'll be okay at that point. So I want to split this. So here's hole number 1. And here is hole number 2. So this is probably, it's a little bit more than 1/4 of a turn past the 9 turn mark. And I'm going to split the difference. What I'm going to do is, on my white piece of PVC, I'm going to drill this in the middle of these 2 points. So I'm going to put it like right about here. And then test it. And we should be very close. Okay, so we'll turn this off to save the battery on the Nano. Nano. And we'll take this apart. So I'm going to pull this out. And I need to drill some more holes. So my first hole, I'll put in the same place. That is a seriously dull drill bit. So I kind of bend that over so the coax doesn't have a kink in it. And then the second hole, as I mentioned, I'm going to split the difference between these 2 points. So it's going to be, instead of here, I'm going to put it up here. And now we can rewind. Be kind, rewind. One, 2, 3, 4, 5, 6, 7, 8, and about 9 1/8. Okay, once again, this is our input, which is the shield. I'm going to make this a little easier because this piece is a little shorter. But we take the shield from the other side. So this goes all the way around. It goes through, and then we take the shield and we run it back through. That's this piece right here. And now we're going to attach it to the center conductor, right where we input our signal. So this is our input. Goes all the way around the form, and we bring the shield back, attach it to the center conductor, and then the center conductor is what becomes our output. So input, output. And now we can retest. And let's see how much it moved. Not much, but it did move. Now, I'm going to go ahead and I'm going to separate just a little bit here. These coils. This is cheating, so you can just put some airspace between these coils of the coax, and it will raise the trap frequency a little bit. See if I can get it to go a little bit more. This is 6.92 megahertz, and I believe that's probably going to be good enough. Let me zoom in on this a little bit. So yeah, I think that'll work. That's 6.924 is where we have our resonance. And you can see this blue trace is impedance. And you can see that little impedance bump. Now, this isn't picking up a lot of it, right? But it's picking up enough of it that we can tell where this trap is resonant. Basically, the signal from the nano VNA is exciting this trap. And wherever the trap is resonant, it creates an impedance rise on the nano VNA. So you can actually test the resonant frequency of the trap in this method. And I think we're good. We're at about 6.9 megahertz, which is just below the 40 meter band. So that should work perfectly. So now, what do we do from here? Well, what I do is I will take some clear coat. I will clear coat this when I'm all done. But I have one more step that I need to do. What I need to do is I will solder an eyelet onto this shield right here. So I've got eyelets out in the garage. I'm going to solder an eyelet. Then I'm going to drill a hole, and it's going to be opposite where the coax goes in. So I'm going to drill a hole here. And then I'm going to put a screw through that hole, through the eyelet, through the hole. So that's going to stick up, and then I can attach my antenna wire to that. So I do the same thing on the other side. I take this center conductor, and in line with this one, this screw, I'll put another screw, drill a hole, solder an eyelet onto this wire, the center conductor. This will be our outlet of the trap. I'll put the screw through the eyelet, through the hole, and then I'll attach my antenna wire going out from the trap to this side. And then to weather seal it, what I use is knockouts. So this is a plumbing knockout. You can get these at hardware stores. And they're designed to go into the pipe. But for 1.5-inch pipe, I find that this knockout, which I don't know the size of this thing, I think it's a 2-inch. A 2-inch knockout will go over 1.5-inch pipe. So all you have to do is you take this little tab and you break that off or grind it off, get it out of the way. And then this will go right over top of this, and it makes a watertight seal when you do that. So you get 2 of these from the hardware store, and when you get done with this trap, you can just put one on each side. Now it's watertight. Keeps the water up. So on mine, what I'll do where the screw comes out is I'll also notch this a little bit so the wire comes straight through here without any chafing against this plastic. Theoretically, you could grind this flange completely off. It would probably look better to boot, but that's how I do it. And this trap, put this in the middle of the wire, and it will block 7 megahertz RF. It won't be able to go past this trap, which is great for antenna building. Now, let's say that you mess up and you make this trap resonant right in the middle of where you want to transmit. So let's say you transmit on 7.250, and your trap is resonant at 7.250. It will still work, but what will happen is there'll be about a dB of loss, because right where this thing is resonant, there's some loss. So that's why you're supposed to set these up to be resonant just below the band edge. So if the lowest you're going to go is 7.175 megahertz, then what you want to do is make sure that this is resonant below that. And I like to go below, because if you go above, if this thing starts to drift with age, sometimes these coils can move around a little bit. They almost always drift higher in frequency. So for that reason, I'll set them up low on frequency. And you could probably go as low as 6.7 megahertz. It'll probably work just fine. But I try and aim for like 6.9 or 7 megahertz. And if it does drift higher, it's going to drift into the band, not away from it. So I'm going to go ahead and finish this one up. I'm going to drill my holes, put the screws in, solder my eyelets on, put the caps on it, tape off the screws so I don't get any clear coat on them, and then clear coat this thing. And the clear coat, if you put 2 or 3 coats of clear coat on this and let it dry, it will lock these turns down so they can't move. And that's the goal here. So also offer some UV protection. But that's basically how you build a trap. And very fun to play with. I mean, you could build trapped dipoles where you have a center-fed dipole with multiple traps in the wires, and it could be resonant on several bands. I've experimented with those in the past. I had the first big fan dipole that I built. It was a 20, 40, 80 meter dipole, and I had traps in the 20, 80 wires. So about 16 feet out on each end, I put two traps that were 14 megahertz traps, which blocked 14 megahertz RF for 20 meters. So those two wires did double duty as a 20 meter dipole and an 80 meter dipole. And the other thing about this, as I mentioned in the last video, is when you run traps like this, they inductively shorten the wire a little bit so it's not as long. So there you go. Thanks for watching, and catch you on the next one.